Hi again, welcome everyone. Today we're very happy to have Pau Figueres from Queen Mary University, London, who's going to tell us about simulating higher derivative theories of gravity. Please, Pau, go ahead.
Well, first of all, I want to thank the organizers for inviting me to give this talk. I'm very excited about it. But before I start, let me just start with a disclaimer saying that there won't be any holography today in this talk, but some of these ideas I'm going to be talking about can be applied in holographic contexts. So hopefully you'll find this interesting. So the topic of my talk is about simulating higher derivative theories of gravity, which arise naturally in the context of say, gravitational waves, but also in holography. So, as I said, so these sort of things, simulating higher derivative theories of gravity, is mostly motivated because we are now in the era of gravitational wave astronomy, and this has offered us the possibility of testing the strong field regime of gravity in a completely new regime, namely in the sort of regime of a black hole binary, the merger of a black hole binary. That's a strong field regime of gravity, which we didn't have access to before. And through these tests, one hopes that perhaps we'll get a better understanding of the fundamental nature of gravity itself. So, in terms of carrying out these studies, one has to be aware of that the current data from gravitational waves indicates that the deviations of GR are small. And the fact that they are small should guide us towards what kind of tests we want to perform. So in terms of testing GR with gravitational waves, one has to be aware of the following issues. So first of all is that to carry out these tests, one needs predictions from the strong field regime of alternative theories of gravity. And at the moment, there are very few of those. And the reason why that's the case is because if you start studying sort of modified theories of gravity, which is something that I only started doing recently, then you realize that it's a Wild West. There are like perhaps more than 100 different theories, alternative theories of gravity. When you talk to different people, they find different ways to motivate them. But the point is that they all modified Einstein's theory in a different way. So presumably, all of them have different predictions for, say, gravitational waves or the strong field regime of the theory. So it's not clear what kind of effects one should be looking for in the signals. And a related issue is that in many of these alternative theories of gravity, it's not known whether the initial value problem is well posed. And if these theories don't have a well posed initial value problem, then it's not clear how to meaningfully extract predictions from this theory. And I'll explain this in more detail later in the talk. So in light of these difficulties, the community has proposed different ways to make progress. So one is that if you have a favorite alternative theory of gravity, then go and find a well-posed formulation of it. And this has been successfully done in a class of theories of physical interest, some of which I'll be talking about today. Another option is to linearize around general relativity. So for instance, you can consider a black hole binary in general relativity, and on top of this, linearize around Einstein. So the advantage of this approach is that it's very flexible and there are no issues with well-posedness, but it has some serious drawbacks. One is that when you linearize around GR, say, then one should expect that secular effects eventually kick in and therefore invalidate perturbation theory in a regime when it should be valid. And also this approach is totally insensitive to nonlinear effects. And those can be important in terms of distinguishing these theories from GR and distinguishing these theories between themselves. And the last approach that has been proposed is to fix the theory a la Müller-Israel-Stewart, as done in relativistic viscous hydrodynamics. And I will also be talking about this approach today. So, because I come from a background in high energy physics, so my motivation to get into this business is not because I like these alternative theories of gravity, but because I want to understand what is the fundamental nature of gravity. And because of that, we know that there is a class of modifications of general relativity that arises naturally from a microscopic theory of gravity, such as like string theory. And these are higher curvature corrections. So in this context, we think of general relativity as a low energy effective field theory of gravity. And then it is very natural that, from string theory, you get higher curvature corrections to the Einstein-Hilbert Lagrangian. And the point is that if you know string theory, you can calculate the coefficients that come with these corrections. So for each string compactification, then you know precisely what type of higher curvature terms you get. And this is quite analogous to hydrodynamics, where we think of hydrodynamics as a derivative expansion around thermodynamic equilibrium, and the series is infinite, and you expand in derivatives of the thermodynamic fields. One other motivation for considering higher derivative corrections is that since those terms are sourced by curvature, one may hope that in the strong field regime, the effects of these terms may be enhanced. But that's a hope. And just to be concrete, I'll be focusing on black holes throughout the talk. And the reason is that if we want to understand about the fundamental nature of gravity, then we should focus on black holes, because these are the simplest objects in any gravitational theory. Other gravitational objects, such as neutron stars, typically involve other non-gravitational physics, which is often poorly understood or difficult to model in practice. So it's less clear how to make statements about the fundamental nature of gravity in these other instances. So I will just consider black holes. As I said, considering this sort of corrections is very well motivated from holography, because if one considers higher derivatives in the bulk, then that corresponds to finite coupling effects at the boundary. And with some of the techniques that I will be discussing today, it is now possible to incorporate these finite coupling effects in interesting scenarios, such as trying to understand the approach to equilibrium through hydrodynamization and finite coupling effects to these things. So I will not be talking about this today, but this is some line of research that we are thinking about with some people today, like Shante Cervantes here. All right. So let me just quickly remind you of how we think about gravity as an effective field theory. As I said, the idea is that we start with the Einstein-Hilbert Lagrangian, and we add all possible terms consistent with the symmetries, namely diffeomorphism invariance, and maybe if you want to add parity and so on. So if you do that, then that's a sort of action that one would be considering with some coefficients that you would need to fix through experiment. But as I said, in specific string theory compactifications, then you can compute these coefficients from first principles. Now, in this expansion, one can remove certain terms in this derivative expansion by considering field with definitions and using the lower order equations of motion. And if you do that in gravity, then in pure gravity, I should stress, then it turns out that the series starts at the cubic term. And also we know from early work by Maldacena and others that there are some issues with this cubic correction, because it can lead to sort of one may be able to construct time machines and so on. So it's theoretically one may actually rule out this term as well, but let's just keep it there for the time being. So as I said, the coefficients only can be determined if you know the macroscopic theory. But in practice, what we do is we truncate this infinite series at the leading order term, say the cubic term or the quartic term. And in doing so, this is only consistent for as long as this leading order correction remains small with respect to the leading order term, namely the Einstein-Hilbert term. If these corrections become large at some point during, say, the evolution of the system, then this truncating this infinite series is no longer justified. So in what we are doing, we will have to make sure that at all times, the corrections, the higher curvature corrections that we introduce, remain small. But this doesn't mean that we have to treat them just in linear theory. So there is another instance in which higher curvature corrections to GR are relevant, and that's inflation. because the early universe belongs to the strong field regime of general relativity. And we know that at least during inflation, at some point, GR had to be modified. Okay, but in the case of inflationary spacetimes, one has a scalar field in the simplest models. So one can do the same game and consider the leading order higher derivative corrections to the Einstein scalar field system. And this is something that was done quite a few years ago by Weinberg. And it turns out that you can show that the leading order corrections to the Einstein-Hilbert Einstein scalar field system are just these two terms, namely a quadratic term for the scalar field and the Gauss-Bonnet term with some coupling that depends on the scalar field, but not on its derivatives. And this theory is supposed to govern the leading order corrections to the Einstein scalar field system. And it has the advantage that the equations of motion are second order. So it's sort of easier to understand from a mathematical point of view. So this is one of the theories I'll be considering today. So the outline of the rest of the talk is as follows. So first, I will discuss the well-posedness of the initial value problem in GR and how one goes about extending it to these higher derivative theories. Then I'll discuss as an example this four derivative scalar tensor theory. That's the theory that should be governing inflation. And then I'll discuss how one can implement this Müller-Israel-Stewart formalism for a genuinely higher derivative theory of gravity with higher order equations of motion, namely the eighth derivative theory. So I'll explain that later in the talk. And as Daniel said earlier, so if you have any questions, just jump in at any time. Okay, so let me discuss the initial value problem in GR first. So what do we mean that the initial value problem is well posed? So by this, we mean that given suitable initial data, the solution exists, is unique, and it depends continuously on the initial data. This is a mathematical way to say that the theory has predictive power. Okay, and that's one basic demand that one should make on any physical theory. Now, together with well-posedness, there is another important aspect of it, which is if a theory is well-posed, then one can control the size of the solution. And by size here, I mean in a suitable, say, functional space in the future based on the size of the solution on the initial data slice. And this is crucial if one hopes to simulate the theory in a computer, in particular in these theories of gravity, which are highly nonlinear. So without this sort of control on the size of the solution, there's no hope that one can simulate these theories in computer. So well-posedness gives us two things. One is predictivity, and second, some control on the size of the solution. Okay, so in gravitational theories, establishing well-posedness depends on basically two things. So one is choosing suitable classes of initial conditions, and second, finding suitable coordinates. So in other words, it's very hard to prove that the theory cannot be well-posed in the gravitational theory, because you will need to show that there don't exist coordinates such that the theory has a well-posed initial value problem. And this is very hard. So what people do usually is that you pick some set of coordinates and then you check whether in these coordinates the theory is well-posed. Okay, so in GR, this was first done in the 50s by Madame Choquet-Bruat, who showed that there exist these harmonic type coordinates. So the space-time coordinates satisfy some wave equations with some sources. And in these coordinates, then the Einstein equations just look like nonlinear wave equations. So they are manifestly hyperbolic. And this formulation is very suitable for in mathematical studies of the theory, because precisely of this manifest wave-like nature of the Einstein equation. So in most works in mathematical relativity, people use like wave-like coordinates. And this has the disadvantage, though, that in practical simulations, then one has to excise the region inside black holes to avoid singularities. But this is technically difficult, perhaps, but is now well understood how to do it. And one point that I want to stress about this formulation is that in generalized harmonic coordinates, all modes, and by all modes here I mean physical modes, constraint violating modes, and gauge modes, they all propagate at the speed of light. And so they are degenerate. And this point is important when one wants to modify GR. The other commonly used formulation of GR in numerical relativity is these ADM-like formulations, or these glorified versions of ADM called BSSN, CZ4. And these formulations use so-called singularity avoiding coordinates. So in these formulations, one makes explicit choice of coordinates, in particular of the time coordinate. So you split the metric into time and space, and the evolution variables are essentially the induced metric on the constant time slices and the velocity of this metric, namely the extrinsic curvature, which is essentially the time derivative of the metric. And the freedom to choose coordinates in general relativity translates into the freedom to choose evolution equations for these two functions, which are called the lapse and the shift, which basically tell you how these equal time surfaces embed into the full space-time. So in this formulation, the key aspect of getting this formulation to work was to find good evolution equations for the lapse and the shift. And in the generalized harmonic formulation that I just alluded to, this is equivalent to choose source functions for the space-time coordinates. So the formulation turns out to be a bit more complicated, so we'll not write down the equations because they are not they're just too complicated. But the point I want to make is that in this formulation, the wave-like nature of the Einstein equation is obscured. So this formulation, while is very robust for numerical simulations, it's not good if you want to study, if you do like mathematical relativity studies and so on, precisely because the equations are not manifestly wave-like equations. So this has two consequences. One is that in this formulation, not all modes propagate at the speed of light. In particular, gauge modes do not propagate at the speed of light, and this can cause some problems. In particular, in this formulation, it's not clear how to impose constraint-preserving boundary conditions. But the advantage is that people have found good evolution equations for the lapse and the shift, such that your time slices do not ever reach singularity. So one doesn't have to excise, and this makes this formulation very convenient for practical calculations. So it turns out that if you go beyond GR and consider higher derivative theories, such as Hordensky is just the most general scalar tensor theory of gravity with second-order equations of motion, and Lovelock theories, like these, again, most general pure theories of gravity with second-order equations of motion, then harmonic gauge doesn't work. So it is precisely the fact that all modes are degenerate that makes these coordinates not suitable in these theories, and that's a rather technical issue. But these authors showed that harmonic coordinates do not work in these for these classes of theories. And what was realized in this work is precisely the fact that in harmonic coordinates, all modes propagate at the speed of light. So in order to get a well-posed system, what Aaron Kovacs and Harvey Rial did was to modify harmonic gauge, giving different propagation speeds to different modes. And the way they did it was by introducing two auxiliary metrics that govern the propagation of the unphysical modes. So what they did is they introduced these, so there's a physical metric governing the propagation of the physical modes that propagate at the speed of light. And they introduced two unphysical metrics such that the light cones are sort of arranged in this way. There's nothing important about the order of these light cones for as long as they do not intersect. So one of these light cones governs the propagation of the constraint violating modes, and the other light cone governs the propagation of gauge modes. And by breaking this degeneracy, then you can show that these classes of theories, Hordensky and Lovelock, are well posed in these modified coordinates, in this modified harmonic coordinate. And what we did in our work was to find suitable evolution equations for the labs and the shift, such that they also achieve this goal of avoiding coordinates in these sort of classes of theories, Hordensky and Lovelock, generalizing the work of Harry Real and Aaron Kovacs. So now we have both modified harmonic coordinates and modified these sort of singularity avoiding coordinates, such that these classes of higher derivative theories, such as Hordensky and Lovelock theories, are well posed. And we can now go about and simulate them in computers. So that's what I'm going to talk about next. So before I move on, are there any questions about this part of the talk so far? Okay, then first of all, I will start now with...
Sorry.
Yes.
Excuse me. Hi, can I ask you a question about
of course.
This? Is there any specific reason why you didn't consider Gauss-Bonnet gravity among these examples of higher derivative gravities?
Well, so in pure gravity, Gauss-Bonnet is topological in 4 dimensions. So it doesn't contribute to the equation of motion, but this 4 derivative scalar theory of gravity is basically Gauss-Bonnet, but with a coupling that depends on the scalar field. Then this makes the Gauss-Bonnet term non-topological. So that's Gauss-Bonnet.
So your study is limited to 4 dimensions and is not in ADS 5 dimension, as you said.
No, that's something we are. What I'm going to talk about today is 4 dimensions, but these are things that we are thinking about, and in our gauge we also prove that these theories are well posed in our gauge, in our working gauges in high dimensions. And ADS is no different. ADS, you only need to worry about boundary conditions, but it also works.
Okay, thank you.
All right, so yeah, so this is the theory I'm going to consider first, and it's 4 dimensions. But as you can see here in the action, then the Gauss-Bonnet term appears multiplied by a coupling which depends on the scalar field. So this term is not topological. So it's in fact it's dynamical. But yeah, so as I was saying, our proof of well-posedness is dimension independent. So it also works in high dimensions. And in this case, in just pure gravity, Gauss-Bonnet in our gauge is well posed in 5 dimensions, for example. Okay, so of course, when one goes about to doing simulations, you need to make, so these, you can see that this action depends on 2 coupling functions, which are functions of the scalar field, but not of its derivatives. So if you want to make some simulations, you have to make some choices, right? And for the scalar field, we just made this function G2 that multiplies this quadratic scalar term. We just made the simplest possible choice, which is just to set it to a constant. And for the coupling function multiplying the Gauss-Bonnet term, we made 2 different choices, and I'll explain why these are the choices we make in the next slide. Okay, but yeah, so that's the choices we made. So our approach is that we treat this theory as a classical effective field theory. So we think about this theory as being sort of an infinite series in derivatives, or in this case of the scalar field and the metric, but we truncate this infinite series at the leading order term. And in order for this to make sense, we need to make sure that at any time during the evolution, the corrections to the 2 derivative terms remain small. Okay, otherwise the truncation is not justified. And this is compatible with the nonlinearities, but is also consistent to neglect the higher derivative terms in the action. And it is only in this regime where the corrections to the Einstein-Hilbert term remain small that these well-posedness statements hold. So, and we'll see this very clearly in the next slide, why well-posedness may fail if the corrections to the Einstein-Hilbert term become too large. Okay, so in our simulations, we make sure that, as I said, the corrections remain small, and this is quantified by what you see here in the bottom of the slide. So we want that the coupling multiplied by some, like the typical length scale of the system, that should be small. And this guarantees that the corrections to the Einstein-Hilbert term remain small. Okay, but we treat them nonlinearly. So why we pick these theories first, and then I will discuss these weak coupling issues. So first we consider, so the equation of motion for the scalar field in this theory takes this form. So it's not the spacetime metric that governs the propagation of the scalar field, but it's an effective metric that depends on the scalar field and its derivatives. And the scalar field is sourced by this term, the Gauss-Bonnet term, and the derivative of this coupling. So in the first class of theories that we considered, these are called the shift symmetric cases in this modified gravity community. And this is because the equations of motion are symmetric under shifts of the scalar field. And if you look at the equation of motion for the scalar field in this shift symmetric case, then this equation has a source. So these theories, so for these theories, the Kerr black hole is not a solution. So you have hairy black holes. Oh, sorry. So for these theories, Kerr is not a solution. So from a phenomenological point of view, these theories are not interesting, apparently. But our motivation was to just get some understanding of what kind of effects one could expect or what could go wrong when in simulating higher derivative fields of gravity. So the second class of couplings that we chose is this exponential coupling that you have here. And the reason why we chose this one is because in this theory, by choosing this coupling constant gamma, suitably, one can show that Kerr is a solution, but you can also have hairy black holes. So you can have different phases, different black hole phases with hairy black holes and Kerr black holes. So you can have phase transitions in this theory. And now let me comment on this weak coupling thing. So in these theories, higher derivative theories, as I said, in this case, the scalar field, the propagation of the scalar field is governed by this effective metric, which depends on the spacetime metric and other terms, which involve derivatives of the scalar field. For the spacetime metric, it's qualitatively the same, but it's more complicated. So let me just focus on the scalar field. Okay, so if you look at this metric, then it's not obvious that this metric is hyperbolic. And if the terms that correcting the spacetime metric become too large, then this metric may not be hyperbolic. And in fact, this is what happens. If these terms become large during the evolution, then the character of the equation changes. It may not be a wave-like equation anymore. The equation may turn elliptic, may turn parabolic. All sorts of things can happen. And also another thing to bear in mind is that these effective metrics are pretty much similar to what happens in fluids, where these fields in the hydrodynamic equations are governed by these effective metrics, which depend on the derivatives of the fields themselves. And in that case, one can prove that even if you start with smooth initial data, shocks can form in finite time. So in these theories, in principle, shocks can also form in finite time, which is something that doesn't happen in GR. Okay, so in order to simulate these theories, so the first thing that one needs to do is to identify the region in the space of initial conditions such that if the theory remains weakly coupled, it starts weakly coupled, it remains weakly coupled in throughout the evolution. So this is what we did in some early work that I did with a PhD student when we study gravitational collapse in one of these modified theories. And it's all you need to take away from this plot is that there's a blue region, which is the region in the space of initial conditions, such that the theory is weakly coupled initially and remains weakly coupled at all times. Whilst in this yellow region is a region in which the theory starts being weakly coupled, but then during the evolution, then the equations of motion change character, right? So if you, in this case, the effective field theory, you exit the regime of validity of effective field theory, so you should not trust this theory in the first place. And all sorts of things can happen. As I said, the equations, the scalar equation may no longer be hyperbolic. It can turn into elliptic and so on and so forth. But as I was saying earlier, well-posedness is an issue of, it depends on two things. One, choosing suitable coordinates, and the other one is to choose suitable initial conditions. So one needs to identify the space of initial conditions such that the theory remains weakly coupled. And that's what we did here. So there is a question.
Yeah, that's great.
Yeah, I have a question concerning these transitions from hyperbolic to
yes.
elliptic regimes and so on. Can you associate these transitions to some kind of phase transitions? Kind of
no.
Dynamical phase transition. Is it possible, or is it not possible here in this regime?
It is not associated to phase transitions. They're typically associated to the theory becoming strongly coupled.
Yeah, okay. Yeah. And there's another question. All your technical approaches, can you relate them to gravity theories, renormalization, and of asymptotic safety, for instance? Is it possible to relate your concepts, or is it too far away?
I'm not sure here what you mean here by asymptotic safety in this context. Can you explain that to me?
You have some, you're choosing some arbitrary background, and then you're yes. considering your nonlinearities about this background, and you're studying under which regimes your theory remains self-consistent or is blowing up or yes. stabilizing yes. or not stabilizing and so on. It's something yes. similar in your case? Or?
Yes. That's exactly what we do. So here we try to identify the regimes in these theories such that the correction remains small. So it's in a way it's like stable, if you want, in your language.
Yeah. Okay. Thank you.
Yeah. Any other questions? Okay. Then let me continue then. So after identifying suitable coordinates and identifying the space of initial conditions such that the theory remains weakly coupled, then we can go about and simulate the strong field regime of the theory. Okay, well, and we did that by simulating black hole binaries. And again, because at this stage we're not interested in like providing waveforms for LIGO, we're just interested in understanding the robustness of these methods and to understand also what can go wrong. Then we just started with superposed black holes. This introduces some initial constraint violations, but that's not an issue for as long as the black holes are initially far apart. Then again, I emphasize that we make sure that the system is weakly coupled initially and remains weakly coupled at all times. So we monitor this weak coupling condition. So in practice, though our coordinates are quite kind of robust, so this weak coupling condition can become order 1 and still works. So that's a good thing. Even though when this weak coupling condition becomes order 1, you should probably not be trusting the theory because there's no justification for truncating the series at the leading order term. But in terms of just testing how robust our coordinates are, then that's good enough. Okay. So first, so this shift symmetric theory, again, it's not that I believe that this theory has anything to do with nature, and if anything, I would like to kill it. But anyway, so in the shift symmetric theory, then so we simulated these black hole binaries, and we got basically what you'd expect, which is that when the couplings are very small, the theory is very close to GR. That's what you see in this, like, so the blue line is GR, and this dashed orange line is this shift symmetric theory. And as you increase the couplings, then you can see that the waveforms become shorter and shorter, which means that the black holes merge in fewer orbits. And the reason why this happens is because this theory has another degree of freedom, the scalar field. So the theory can radiate very effectively in the monopole and dipole, which is something that you can't do in just pure GR. So this theory can shed energy and angular momentum more efficiently than GR. So as you increase the couplings, then basically the black holes merge very quickly. And so in this red waveform that you see here, basically the couplings are such that this weak coupling condition is order 1. So So anyway, so this shows that this theory is robust. So our coordinates are robust. So the other theory, this exponential coupling theory, that's phenomenologically more interesting, because in here, what we did is we started with just black holes with no scalar field. So we started with a configuration which is just basically GR. So these black holes were non-spinning black holes, and they merge just as in GR. There's no scalar field initially, so you could not tell this theory from GR in the inspiral phase, and then they merge. And then when these two black holes merge, you can see the top panel is just the tail of the waveform. So the black holes form a curve like black hole. It rings down through the standard quasi-normal mode. And once this black hole has settled, then all of a sudden you can see an instability. So the scalar field grows, and you can see a very strong scalar wave, which is which is axisymmetric, and the black hole scalarizes. So this is an instance in which you would see throughout the inspiral and merger phase, you would see GR, and only after the merger you would see scalarization. So this phenomenologically could be interesting, because you would not be able to tell this theory apart from GR if you only looked at the inspiral and quasi-normal mode phase. So here's just a simulation of what happens. So you've got two black holes orbiting, and as I said, at this stage, this theory is indistinguishable from GR. Then the two black holes merge, and this black hole settles, and all of a sudden, boom, a scalar cloud forms, and it settles onto a hairy black hole. And one can see this also on the so the left panel is seen from the top, and the right panel is like a cross section, and you can see that the scalar cloud forms around the axis of rotation of the black hole. It's like a mushroom. And the reason why this happens is because the scalar equation is sourced by the Gauss-Bonnet term. And if the black hole is spinning sufficiently fast, the Gauss-Bonnet term can change sign on the horizon, and it becomes negative first around the pole or in the region around the pole. And this drives an instability, a tachyonic instability for the scalar field. And this only happens if the spin of the black hole is sufficiently fast. Around 0.7 is when it changes sign or something like that. Okay, so if you start with non-spinning black holes, then a spinning black hole forms after merger, and then it becomes unstable to scalarization, and that's what happens. Okay, very good. So this is just to illustrate our methods for these classes of theories with second-order equations of motion. But now we want to move on to, in my opinion, the real deal, which is like theories with genuinely higher derivative equations, so higher than second-order equations of motion, and how we sort of dealt with these classes of theories. So before I move into this, are there any questions? Okay. So here we considered the most general theory up to 8 derivatives. I said the cubic term that I mentioned earlier, because of the work of Maldacen and others, one can argue that one can sort of, if that term was there, you would be able to build a time machine and so on. So let's not consider it. So if you then rule out this term, and in fact, if I'm not mistaken, in type 2B compactifications, you don't get a cubic term. You start getting only quartic terms and so on. But anyway, so we just took this theory as an example of a higher derivative theory. And if you consider the expansion up to 8 derivatives, then you get these are all possible terms that you can get. And one is like Kretschmann squared, and then the other one involves these the dual Riemann tensor. And out of these 3 terms, the last term breaks parity, whilst the other 2 don't. But just for the sake of concreteness, then we only consider the first term. Okay, and the equations of motion for this theory are of 4th order. So you can see here on the right-hand side that there are terms involving 2 derivatives of the Ricci and 2 derivatives of the Kretschmann. So these are like 4th order equations of motion. And I want to stress that there is no mathematical theory for the existence, uniqueness of solutions of PDEs of higher than second order. So the question is, how do you make sense of this theory, or how do you meaningfully extract the predictions of this theory seen as a low energy effective field theory of gravity? So this is what we want to do, okay? So we're not interested in thinking of this theory as the ultimate theory of gravity. So we just want to be able to study what kind of long distance corrections this theory can introduce to the Einstein-Hilbert, to the usual general relativity, okay? So whatever we do, it cannot, in a way, it cannot depend on the sort of high energy details of the theory, or the sort of the UV completion of the theory. So this is very similar to what happens in relativistic viscous hydrodynamics. So if one considers just a conformal relativistic fluid, and you expand the stress energy tensor up to second order, then that's what you get. So here you have the stress energy tensor. That's the first term, is the ideal term, and then you've got the viscous terms. So with the usual shear viscosity term, so this sigma is the shear tensor, and then you've got second order terms, which involve the derivative of the shear tensor. So these are second derivatives, and then you've got also the vorticity tensor. Okay, so this is the expansion of the stress energy tensor to second order of a conformal fluid, and the equations of motion are just the conservation of the stress energy tensor, and these are just third order equations. Okay, so again, so how does one solve these sort of equations, or how does one make sense of this theory? Because it has all sorts of problems related to like well-posedness and so on and so forth. All of these problems arise in relativistic hydrodynamics. Okay, so and how do we make sense of this? So the proposal of Miller, Israel, Stewart was to promote this viscosity tensor to a new dynamical variable. And if you do that, you need to provide an equation of motion for this new variable. And what they did was to provide a completely ad hoc equation of motion for this variable, which is the one that you have written here. So this equation has two important features. So one, this equation is such that this viscosity tensor evolves towards the shear tensor in this way, and it does so on a time scale set by this one of these transport coefficients. Okay, so this is not a wave-like equation. And the other feature is that by promoting this variable to a new dynamical variable, then one reduces the order of the equations of motion. So now the order of the equations of motion is just first order. Okay, so one can, again, now you can use the machinery, mathematical machinery, to prove existence of solutions and so on and so forth in principle. Okay, so you can show that this is now can be a well-posed system that you can hope to solve in a computer. Okay, and I should say that in hydrodynamics, the transport coefficients are computable from a microscopic theory. So in principle, this transport coefficient tau, it depends on the microscopic theory. So it's something that one could know.
I mean, excuse me.
Yes.
Just as a comment, it's not really ad hoc, right? I mean, it has a link to thermodynamics, equilibrium thermodynamics, and basically they're relaxational equations, which is why Kubo formulas are well defined. There is some leeway in how to choose the coefficients.
Yes, that is true, and the coefficient are chosen such that the entropy current has positive divergence and so on and so forth. So it's not totally ad hoc, but it's definitely non-unique.
Yes, yeah, that's true.
So now we want to do something similar for this high derivative theory of gravity. Okay, so the first thing that we do is to just use the lower order equations of motion, and the previous equation of motion, the Einstein equations, tells us that the Ricci tensor is order epsilon. So the terms that appear on the right-hand side of the Ricci tensor would contribute to order epsilon squared to the equations of motion, so we drop them. So we only keep the terms that depend on the Weyl tensor. Okay, so this simplifies the equation to what you have here, and it's still a fourth order equation. Okay, so we have the same problem as before. And what's in our shopping list? So first, we want to modify this equation such that the resulting equation is well posed. The second thing that we want is we want to consistently incorporate these higher derivative corrections in a way such that we can compute meaningfully the long wavelength effects, but at the same time we control the flow of the energy to the UV. In other words, we do not want our solution to depend on the UV completion of this theory, because after all, once we do this modification and turn this into a well-posed system, what we are doing is artificially coming up with a UV completion. So we do not want our physical observables to depend on how we UV complete the theory. Okay, and also by doing this self-consistently, we want to capture the nonlinearities of the theory just whilst making sure that the corrections to the Einstein-Hilbert term remain small at all times. Okay, so this is what we want to do. So in order to make progress, it's useful to sometimes consider a model problem that one can sort of try to understand. And a model problem for this case turns out to be just a scalar wave equation modified by a fourth time derivative on the right-hand side. So if you go to the previous slide, there are like 4 time derivatives of the metric in the last term here on the right-hand side. So the space, like the space derivatives are not so much of an issue, because typically they would lead to like diffusive like terms, so they're not so much of a problem. But okay, so that's why we sort of model this with the 4 time derivatives, which are more dangerous. Okay, and then now we want to apply a MIS type approach to this model problem. So we can do it in 2 ways. So one is one could say, well, if we use the lower order equations of motion, then we could modify the right-hand side and reduce the order of the equations such that we trade 2 time derivatives by 2 space derivatives from using the lower order equation of motion. So that's option number 1. And option number 2 is that we do this twice. So we modify these 4 time derivatives by 4 space derivatives using the 0th order equation. And this, depending on the sign of epsilon, this would look like a diffusion, a higher order diffusion term. But if you analyze these solutions, then it turns out that one can show that in general, you have blow-up solutions in both cases, option A and option B. So how do we fix the problem? So in this case, as I said, if you do a MIS type theory, then we modify the right-hand side and we promote this to a new variable, whilst at the same time reducing the order of the equation. And in this case, we provide a completely ad hoc, completely ad hoc, not totally, but we provide an equation of motion for this new variable. And we design this equation of motion such that the new variable, C hat, which is unphysical, evolves towards the physical variable, which is, in this case, the 2 space derivative of this field, on a time scale set by these 2 parameters, which are now arbitrary parameters, right? So these parameters we do not know of the microscopic theory. One may hope that in a microscopic theory, just as in MIS, these parameters could be related to some transport coefficients, but of course, at this stage, this is something we don't know. So in this case, we've also added these advection terms. So this d0 is the time derivative plus an advection term. And we do that because when treating black holes that move around, having advection terms is important to make sure that things fall into the black hole at the right rate. Okay, and it turns out that with this theory, one can show that this new variable C hat remains close to the physical variable. This is a 2 space derivatives by choosing this parameter sigma and tau suitably. And one can show that the solution does really remain. These parameters do not have an impact into the way the solution actually looks. So bottom line is that with this sort of fixing equation, we have a well-posed system. And moreover, we can guarantee by choosing these parameters that we can self-consistently simulate this theory and capture the long distance modifications that this exotherm on the right-hand side introduces. Okay, so now we want to do the same for the gravity theory. And our proposal is the following. So we promote this variable that you have here to a new dynamical variable, this curly C hat. And we provide a very similar looking equation of motion, which depends on two parameters, sigma and tau. So this achieves two things. So it reduces the order of the equation, so that now only second derivatives appear. We also have second time derivatives hidden in the Ricci in the Weyl tensor here, and we replace those by using the lower order equation of motion. Okay, and then one can see that with this new equation, we can see that this new dynamical variable C hat remains close to the Kretschmann, which is this curly C, and it does so on a time scale, which is set by this combination of parameters. And the point is that one can choose these parameters such that this time scale is much faster than any of the physical time scales in the system. So in doing so, we can hope that we can self-consistently model this higher derivative theory. And furthermore, the other thing that we need to check is that any physical observables is not sensitive to the choice of these parameters sigma and tau, whilst is sensitive to the say coupling constant, right? Because that tells us that we are incorporating the corrections to the Einstein-Hilbert term in a consistent way. Okay, so that's what we did, and in this plot, it's just a numerical experiment of see how this equation does. So what's shown here is the top panel is the solid line is the physical Kretschmann, and these dashed lines are these other unphysical variable for different choices of parameters for a case of a black hole which is boosted with some momentum px. So the black hole which is moving in one direction, and this variable trails, the unphysical variable trails or tracks the physical variable. And what this plot shows is that by choosing these parameters, then these variables agree better and better in the region outside the horizon. Of course, what happens inside the horizon is really not important because GR breaks down inside the horizon anyway. These higher derivative theories will behave will also behave badly inside black hole horizons or near singularities. So what we really care about is that in the region is that our equation ensures that the unphysical variable approaches the physical variable in the regions on and outside black holes. And the lower plot shows the L2, the difference between C hat and C in the L2 norm for different choices of our parameters. And one can see that if you make these parameters suitably small, then the tracking becomes better and better. Okay. So once we show that we can simulate robustly moving black holes, and we can make sure that the unphysical variable tracks the physical one in a quantitative way, then we can go about simulating black hole binaries.
Sorry, may I ask a question?
Yes, sure.
When you say the unphysical variable simulates the physical one, don't you need to have a solution for the physical one that would depend on the theory you are trying to solve?
So what I mean here is that, so here what we did in the equation was trade the Kretschmann by a new variable. Mm-hmm. So what we want is that our new variable remains close to the Kretschmann. And if that's the case and the correction remains small, then one would hope that this is modeling a solution of the full theory. Because, so you see, in these effective field theories, you would have like an infinite series, right, of correction. So only if you know the full theory, you can say, well, this is a solution, mm-hmm. right? So what we want to do is with our approach is to hope that with our approach, we can capture the long distance effect of the full solution, for which we don't know. But the fact that our method is self-consistent is indicative that we are really staying in the regime of validity of this theory. So therefore, it makes sense that we can meaningfully truncate the infinite series, And by doing so, we hope that we are capturing this theory. But of course, I mean, what you say is true. You need a full solution of the theory, and we don't know.
Okay.
But the same is true in hydrodynamics. So it's the same thing as saying in hydrodynamics, you want to make sure that your system remains in the regime of validity of hydrodynamics. That's basically what we're doing here.
Mm-hmm. Okay, thank you.
Now, of course, in hydrodynamics, if you by a holography, you have, in principle, you have the full solution, right? So then you can make these comparisons like very quantitative, right? In this case, we don't have the full solution. So it's hard. So what we can do is to model, to make sure that what we're doing is self-consistent. So are there any other questions? Okay, so if not, then I'll just show you just one simulation of a binary black hole in this theory. So the color code is basically the Kretschmann, well, the unphysical Kretschmann, but you cannot tell the physical from the unphysical one on this scale, and this black line denotes the apparent horizons of the black holes. So yeah, as I was saying, by choosing these parameters, then you cannot tell the dynamical, this unphysical variable from the Kretschmann on this scale. So yeah, so we can simulate black hole binaries in these theories. And one feature that is, in my opinion, relevant is that because these theories radiate differently than GR, so depending on the size of the couplings, you have that the waveforms either advance or become retarded with respect to the GR waveform. So in this plot, the GR one is just a blue line, and the other two correspond to two different values of the couplings. So what seems to be happening in these theories is that even though the corrections are small, in a lifetime of a binary, those small corrections can accumulate. And you can end up with large deviations or deviations which are much larger than the size of the coupling constants, just because of these cumulative effects. And only by modeling these theories fully nonlinearly as we do, one can make sure that you can capture those cumulative effects. This is something that you will not be able to do if you did this perturbatively around GR. Okay, so that's something, that's basically what these theories, one signature of these theories, namely this advancement or delay of the mergers, which makes sense physically because they have more degrees of freedom. Okay, so since I'm running out of time, let me just quickly conclude. So we found robust ways to simulate the strong field regime of higher derivative theories of gravity, and we've shown that this works in the case of black hole binary mergers. And in all these theories, we see that even though the corrections to GR remain small at all times, then you can have large deviations in non-local observables, such as waveforms. And there are several lines in which we are thinking about. One can consider just higher derivative theories of gravity in high dimensions, where these lower log terms that become dynamical. That's something that we're thinking about in terms of the Grigorov-Lam instability of black strings. But also, as I said earlier, one can do this in ADS5 and study finite coupling effects. And that's something we are thinking about with Xande Serantes, which I think is here, and some others. So there are some avenues for applications to holography of what I've been telling you today. So, well, I'm done. Thank you for your attention.
Thanks a lot, Pau. Very, very nice, very clear, interesting talk. We've had some questions, but please go ahead and ask some more questions. Giorgio, you don't need to raise your hand. That's the question.
Oh, okay. No, just sort of as a this question was asked during the talk by somebody else, but just to rephrase it a little bit in a slightly different way. I mean, intuitively, your conditions for well-posedness look very similar to the conditions of a quantum theory for renormalizability. In particular, your second condition, the fact that the functional space, you can isolate a functional space where the theory is valid. This is exactly the condition that you can use a few renormalizable terms, and then you have an infinite number of renormalizable terms that do anything and don't, that will never do anything. Mm-hmm. In addition, in classical physics, there is something called Ostrogradsky's theorem.
Yes.
which I think you are sort of using it. I don't, maybe you mentioned it, but
I didn't mention it
a lot. The reason why you generally need new degrees of freedom is Ostrogradsky's theorem and Lagrangian hydrodynamics. One can prove it. And that's related to something also related to renormalizability, but from a slightly different point, which is that the appearance of ghost states, that generally classical instabilities mean. Yeah. Is there a systematic, I mean, the usual renormalization group is in Euclidean space, and of course you're working in Minkowski space, and maybe that, as far as I know, asymptotic safety is also defined in Euclidean space. No, I was just wondering whether in the literature anyone, developed these things more systematically, because it's, from an outsider.
Yes. Yes.
From a semi-outsider, this looks obvious. Yeah.
Yeah, I know. I think that's a very good point. So indeed, I was using Ostrogradsky's theorem without mentioning it. That's indeed the case. To the best of my knowledge, no one has phrased this in terms of renormalization group. That's the honest answer. And in terms of the ghosts that you alluded to, this quartic theory that we are treating basically has you can show that it has a scalar ghost, or has another scalar degree of freedom and a traceless and a spin 2 degree of freedom as well. And depending on the choice of the sign of the coupling, one of the two is a ghost. Okay, but the masses of the ghosts are basically proportional to the UV cutoff scale. So if you model this theory self-consistently as a low energy EFT, the fact that this theory has ghosts should not be relevant, because you should not be exciting the ghost in the first place. So what our method in a way does is to make sure that there is no strong UV cascade that can excite ghosts. And in our way of fixing the theory, what we're doing is we're incorporating these scalar ghost degree of freedom.
Okay, thanks. That was clear.
Okay, and exactly in the same direction, in this concerning Ostrogradsky approach, you have in this PT symmetric theories, you are able to consider phase transitions there in this Ostrogradsky approach. So you are seeing that you can pass from one regime to another regime and reinterpret this as a kind of a phase transition. So this was also the background why I was asking whether you can relate your theory with some kind of phase transition in a dynamical way. So I'm wondering, did you go in some detail in this direction or not yet?
No, we did not.
Oh, okay. Well, thank you.
Yeah, thank you.
Good. More questions? Okay, no more questions. I will stop the recording and ask again. But first, let me thank Pau again and everybody who has questions, but especially Pau for a very nice talk. And see you next week.
Thank you.